All right, folks, I have a bunch of exams that people haven't picked up, so it's it's L-I-U, I believe, Peng Lu here. P-E-N-G-F-E-I. No. Christopher Blake Stafford. Christopher Blake Stafford. No. Zilang Zhang. Zhang Lu L-I-U. Hunter Lasby. Ryan Reyes or Byron Reyes. Is that you? Byron. Anybody else not get their exam back? Sorry. Second thing I want to talk to you about is I got to get your MATLAB projects back through that special extra credit. I'll have them on Monday, and I apologize for not getting them back. It's left on the back burner. It's up in my office. I'll bring them back and take care of it. Now, next thing, questions about anything related to materials stuff. Yeah. Because we've got, well, we did, using the rotated Smith chart, we matched inside the circle, inside the rotated circle, and then I started with outside of both, but I said there's 4 possibilities. Those are the easy ones. You can't go wrong. I mean, well, you can go wrong, that's hard. So, and did you all bring rotated Smith charts with you? How many have them? Who does not have them? All right, could we, those that have them, we're not, before the quiz, could you share some of them, or I'll have to go up and get some. All right, you got one? Anybody else need one? Anybody else need one? A rotated Smith chart. Anybody else? You need one? Can you get him one? Yes. Can you give him a rotated Smith chart? Everybody else has rotated Smith chart. All right. All right. Now, go ahead with your question. What's that?
I was trying to think about
I mean, you know, they're all fundamentally the same thing. You normalize, you plot it. If it's inside the one circle, you go to the other.
I like the way that they fix this question, so I'll go with it.
I was going to say something.
Well, we have to know how to find the total.
What?
The total of minutes.
Well, once it's matched, the input impedance is just Z'd on, right? That's the whole idea. That's the idea. Okay, go ahead.
It was a ZL of 100 minus J 80 ohms.
So we have 100 minus J 80 ohms.
Yeah.
That's your load impedance. Go ahead. What's the match?
Characteristic impedance is 50 ohms. It's operating at a frequency of 11.2 gigahertz.
11 for what?
18.
8 gigahertz. Sorry, that's a smart frequency. But
And it asks to design an L-section matching network that allows for DC biasing of the load element.
hint, allows for DC biasing. Means an inductor in series, a capacitor in parallel. Y'all hear me on that one? That's all it means. Because if you DC bias, you want the current, the inductor looks like a short to DC, right? And a capacitor looks like an open, so it would allow that. In other words, if you're using this to feed the front end of a BJT, you could do that and still have DC bias current going through. All right, now when we do this one, so let me draw my pseudo-Smith chart up here. That's the article 1 circle. First thing I have to do is what, class? Right. So we get ZL equals 100 minus J80 over 50, right? That's 2 minus J, and it's going to be 1.6, right? Isn't that right?
Yeah.
All right. Now we plot that. So in this circle, it's inside the one circle. The two would be probably about there, but I'm just estimating. And the minus J 1.6, if that's minus J 1, this is about minus J 1.6, something like that. So I'm just kind of eyeballing, that would be ZL, correct everyone? When you do this on a Smith chart, label that as 0.1 and circle it, so I know where you start. Because half the time, I don't know what you're doing. I'll see lines drawn this way and that way, and I don't know what you're doing. All right, but you all follow me, that's the first point. Now, it's inside the one circle, correct? We have to go to the admittance domain. So, we go right through it to the conjugate point. Over here. And then I better draw my rotator. Well, this is kind of a lousy looking circle, but you get the idea. And this is going to be YL, that's 0.2. YL here is 1 over ZL. What is that? Can somebody see that?
Rounding, it's about 0.3 plus J, 0.24.
Okay, confirm that anyone? Did you get that? All right. Now we're in the admittance domain. I'm here, I can go two ways. If I go this way to this point, remember I'm going to be on the point, or the 0.3 circle right here. It would be 0.3. If I go this way, I have to add negative admittance, correct? That would be an inductor. That would be in parallel. That would be bad. Follow me the way he stated. He wants an inductor in series, a capacitor. So we're going to go this way. So here's my 0.3 right there, the third point. And it's on the one circle. Can you give me that value? Y'all follow me what I'm doing? I know we've done it several times, but I just gotta make sure. All right, so what's that value? Yeah, look it up on your, you've got one. You can probably enlarge that and really see. So what do you?
0.46 or 0.46?
So it's 0.3 right here, 0.3 plus J, what is it?
0.4.
0.4 what?
6.
All right, so that means I have to go from J.24 to J.46, right? Y'all with me? So what is that? That's 0.22, isn't it? So that means the admittance, normalized admittance here is going to be J 0.22. I have to add to that. Do you all agree with me? Take a moment, just make sure there's absolutely no confusion about this. Now, we go to the impedance domain. In other words, you're taking 1 over that. We're here, this is the third point, right there. So it's gonna come in, it better land on the one circle. It had 1 minus J something. What is that? Y'all follow me?
1 minus J 1.52.
1.52%.
1.52.
1.52. Anybody else confirm that? Y'all with me? All right, now, once I have that, I've got to get rid of this minus J 1.52, right? I do that by adding a plus J 1.52, normalized impedance. Do y'all agree with that? So this is going to be plus J, and it's going to be 1.52. Now, that is all normalized admittances and impedances, and it's matched from here on back. Those are two elements. Now we have to get the values. I always recommend you start with impedances of the elements and then normalize them, then get the normalized admittance. That's just me, because you won't make mistakes that way. So, for this one, this is an admittance, and so I know it's gonna be a capacitor. I start with capacitor. Capacitive reactance is 1 over J omega C. Then I normalize it, divide by Z naught, that's what normalization means. Now that's the normalized impedance, 1 over that is the normalized admittance. Do y'all agree with me? So this is gonna be J omega C Z naught is equal to this value, J 0.22. And therefore, I can say that C is equal to 0.22 over omega, right, and Z naught, or it's going to be 0.22 over 2 pi times F, and it doesn't imply F, 11.18 gigahertz, times 10 to the 9, times Z naught, and Z naught is 50, right? So what do you get for that value, C? What'd you get? Anybody?
6.26 times 10 to the negative 14.
Is that right? 6 point what?
6.26 times 10 to the negative 14.
I noticed a bit of a difference between the question in the textbook and the answer solution, and the answers that you sent to us. They had a 100 plus J80 ohms as the initial value in the answer. But the textbook had a minus.
Well, wait, is that,
That's what I got.
that's the right answer for the assumed values, right? They're probably, I mean, Whitmer's book, he's not, infallible, it's probably a mistake in the way he stated the problem, but it doesn't matter, let's just finish this out. By the way, you see that value? That's not realizable. That is so small. When you're talking about stuff that is hundreds of a picofarad kind of deal, all right? Forget that. You're not going to have a capacitor like that. You've got to do something else with matching. And that comes later. But now, that would be the right value if you were going to do L section matching for that. That frequency is an odd frequency, by the way. All right, that's pretty high. That's basically X-band radar, but it's the higher end. Oh, okay, so now we've got to do over here, the impedance, right? It's J 1.52, it's normalized. So I start with my inductor, it's J omega L. That's an inductive reactance. If I normalize it, I divide it by Z naught. Do y'all hear me on that, everyone? So divide by Z naught. Now that's normalized, and that has to equal that, which is J 1.52. So that means my value of L is 1.52 over omega, or 2 pi, and then it's times 11.18 times 10 to the 9th, and then it's going to be multiplied by Z naught or multiplied by 50. So what do you get for that? That's small too. What do you get? 1.3. That's small too. Okay. Y'all agree with that? All right. So that was that problem. Did you have another one? I figured somebody at least had one they didn't understand how the answers fell through. I mean, is that what you got, by the way?
Yeah.
That's right. I mean, if we did the math right, if we punched in the right values, that's right. Okay. Go.
How would you go about matching it? Really actually doing the matching, like something like that impedance? If an L section like this is too small, but
Well, for this one, I'm going to tell you this much. When you're talking about a value that small, what you're probably going to do is actually just use a short stub to achieve that. Yeah, probably. I'm saying it depends on the situation, but you got to realize that's very small. When you're talking about a value that small, yeah. I mean, 10 to the minus 14.
I've got a question. If you have an inductor in parallel, how did you find the Is this the same formula?
You mean if we're in the admittance domain and we're going to get a negative admittance added, so it would be a parallel inductor? Is that what?
Yeah, if there's not much impedance.
Okay, well, impedance, the way I always say this is, why don't we do that? We'll do the bad design. This is the one, don't do this. But eventually, I'm going to ask you. Is there an eraser that I'm not seeing somewhere?
you can use this one.
Half an hour, I've got it. What they do, thank you though. All right, let's do the bad design.
It's a pretty whiteboard.
Don't you use
Ridiculous.
This is my eraser.
saying this is my toilet paper.
Oh, no, absolutely not.
Yeah, it's way different. What about the whiteboard you have?
Tell you what, let me, this thing, that's pretty dirty. All right, now we do the bad design. That was 100 minus J80, right? To be matched into Z0 equal 50. Now we're going to do the design where we're going to put an inductor in parallel and a capacitor in series. So the first thing is we take this and we normalize it as before, and we get the normalized ZL, which is capital ZL over Z0. And that's equal to 2 minus J 1.6. We plot that point somewhere around here. And that's my first point, right? Then I go to the opposite. I can't get to the one circle no matter what value of J I add here. So I have to go to the admittance domain. Now that's point 1. Now I come through here and I go to the admittance domain. That's my second point. And that's just YL is 1 over ZL. And that was 0.39 plus J 0.24, I think. Is that right? Alright, now we're going the wrong way, in a sense. We're going to go not to this point, but to this point. So we come down here, we stay on the 0.3 trajectory, and we find this point here, and that's going to be 0, this would be my third point, 0.3 minus J 0.46, is that right? 0.46? 0.46. 0.46, correct, class? You all follow me? You're asking about this, I hope you see this. Now we're going the wrong way in a sense. We're going to put an inductor in parallel, which we shouldn't, but we did. Alright, we take a look at the difference, and how much is it? Now this is in parallel. Well, I started at 0.24, correct? And I had to get down to negative 0.46. So that's going to be what? 0.68, or 0.7, pardon, 0.7. So this is going to be minus J 0.7, right here. Y'all follow? Okay, now we're here. That's 0.3, now we gotta take 1 over that, and it better be a 1. So this is going to be 1 plus J what? Should be the same value we had before, only with a plus J. Instead of this. 1, 2? Is that right?
1.5.
Okay. 1.52, correct, class? Now we've got to get rid of this, right? Now we're in the impedance domain, correct? We've got to add a minus J 1.52, right here. And then we'll be matched, okay? Now, so now, does everybody follow? I did the same method, but I went the wrong ways in a sense. I've got an inductor in parallel, and I got a capacitor in series. Now I'm going to get the value of this, right? And that is an admittance, correct, class? It's in parallel. So for inductive reactance, it's J omega L. When it's normalized, it's Z0, divided by Z0. That's the normalized inductive reactance. Take 1 over that, and I get the inductive admittance. So I have Z0 over L over omega with minus J, and that's going to be equal to minus J 0.7. Does everybody follow me? Okay. Now I'm going to figure out the value for L. And I can go ahead and say that L therefore is going to be equal to 0.7. Oh, I'm sorry. L is going to be equal to Z0 over omega divided by 0.7. And here, omega, of course, is going to be, omega is just 2 pi times 11.18 times 10 to the 9th. So, and Z naught is 50. Can you tell me what you get for that? I just am curious. But you all know what I'm doing. What did you get? Say it again.
1.02 nanohenry.
Y'all follow me? All right. How about, how do I get this value right here? That's a series element. It has a normalized impedance of minus J 1.52. It's going to be a capacitor, right? So capacitive reactance is what? I do it this way. I start as 1 over J omega C. Then I normalize it, divide by Z naught. That's the reactance, right? Therefore, what is that? Oh, I'm sorry. This is what I need. My bad. That is the normalized reactance. This becomes minus J on top. And that's equal to minus J 1.52, right? 1.52. You can figure it out from here. C is equal to what? 1 over omega Z naught and 1.52. And what do you get for that? That's going to be small as well. Pardon? 2.2 picofarad? 0.2. Anybody else? 0.2. All right, 0.2 picofarads. That's small. Okay, I don't know. I think in his book he just, well, he's using values that are a bit odd. Okay. Another one? You got any other questions? All right, remember, again, one last thing. If you're inside the normalized impedance, inside the one circle, you've got to go to the admittance domain. First element is in parallel. If you're inside the rotated circle, first element is in series, right? It's an impedance, all right? If you're outside of both, it doesn't matter. The only thing you got to remember is what you're doing. If you're in the impedance domain, if you're out here and you want to move in the impedance domain to here, that's going to be a minus J you're adding. Follow me? If you're down here and you want to move this way, it's a plus J. So you have to keep your head on straight about what you're doing. If you're moving with impedance or admittance, and that's the only thing I'm going to tell you. Okay? All right. You don't? No other problem? Did y'all do that one problem we were doing last class? Did I broke it up? There are 4 solutions to that one. They take a little time, but it's helpful to do them. Make sure you understand it. Okay. So, if there are no further questions, now we're going to move into something called S-parameter matching. I'm going to remember your H parameters. HFE forward gain. You remember this? Reverse gain. Didn't you have H parameters? In analog. You had analog. You remember GM? Yes. All right, all this road. Those are H parameter ways of describing a system. We're going to use S parameter. This is the most common way, and the two are interchangeable. So, I'll use this again. This is it starts on page 557 in your book, and it's S-parameter matching. So we start by saying we're going to be talking about 2-port systems, and it's just going to be a block diagram here. This is going to be a transmission line connected on that side and this side. This is port 1 on this side, and this is port 2. And these are going to be S parameters in here. Now, just understand, these are transmission lines. They're not just wires. They represent. Here on port one, you're gonna have some wave coming in, that's labeled V1 plus, a signal, and you're also gonna have a reflected signal, and that's gonna be V1 minus. On this side, where port two is, you're gonna have some voltage coming into it, and that would be V2 plus, and you're gonna have a voltage waveform that's scattered through there, V2 minus. That's going away. Do y'all follow? Now, the way that these things are defined in terms of S parameters, these S parameters are going to be a 2x2 matrix. And the way it works is this. V1 minus is equal to S11 times V1 plus S12 times V2 plus. And V2 minus is equal to S21 V1 plus S22 V2 plus. Okay? Normally the way it's shown is V, and it'll be just that, is equal to S double bar times, it'll be V minus, pardon me, is equal to V plus. So it's normally written in a compact form like that. How many have seen S parameters? Anybody? Where'd you see them? What class?
It was in a class for research.
Did you?
I have to look at that.
Okay, well, all right, so you haven't been exposed to this in a classroom environment yet, not in your labs or anything. Sometimes you are, all right, it depends who's teaching, I think. But you did have, you all took analog, right?
Yeah.
You remember the forward current data and all that stuff? You all had that, right? But really, there are relationships of either voltage or current in systems defined by S parameters. This is standard conventional S parameters. Now, if you look at this carefully, you can see one thing. You can take a look at S11, and that's equal to V1 minus over V1 plus, given that V2 plus is equal to 0. That's a reflection coefficient. Now, I gotta explain this to you. If you think about reflection coefficients, if there is no V2 plus coming in other words, that port is basically null and void, it doesn't do anything, then the signal coming in here times the reflection coefficient is this reflected signal. Do y'all follow me? So that is the reflection coefficient, and you can even put it as simply the reflection coefficient of port 1, assuming that out here we have what's called a match condition. Now, I didn't put this down there, but it's assuming the lines here have a characteristic impedance, and this is Z naught here. So really, when we say V2 plus is 0, it means that the signal, once it goes through this port system, it's coming out, there's no reflections. It's matched over here. Right? That's what it really means. So that's what S11 is. S22, it's symmetric, is simply V2 minus over V1 plus, given that V1 plus is equal to 0. What it really means is now I'm looking over here, I'm going to get the reflection coefficient of this port when any wave passing through here will not return. It's basically matched. Do y'all follow me on this, class? Now, something that could happen that would make it unmatched, if I put a short circuit out here, then as the wave passed through here, then it would reflect back and come back. There would be a V2 plus. Do y'all follow me? Or V1 plus. So that's why I'm putting this V1 and V2 plus equal to 0. And this would be the reflection coefficient on port 2. That's just what it is. Now, if you, what did I do?
Sorry. Should that be V2 minus?
This should be, now that should be V2 plus is 0. This should be V1 plus is 0. That's right.
But is it V2 minus over V1 plus? Or is it
No, I'm sorry. You're right. My bad. I'm sorry about that. My bad. Okay, now, the next one is called a forward voltage gain. When you look at S21, right there, S21 is equal to V2 minus over V1 plus, right? Assuming that V2 plus is 0. Now, I want you to just take a look at this for a second and appreciate it. We've got, assume a voltage is coming in here, it's got a certain value. When you multiply that by S21, that's going to be the value of the voltage coming out here. V2 minus. Do y'all follow me? V2 minus is going that way. Do y'all follow me? That's the forward voltage gain. And you can even write that down. This is just the forward voltage gain. Everybody with me? Now you have that, actually they do current gain more than voltage, but you can get a voltage gain on your amplifiers, your transistor amplifiers. It's the same at microwave frequencies. Finally, anybody want to take a shot at what S12 is? That's V1 what? Minus over V2 plus, assuming that what? V1 plus is equal to 0. It's the reverse voltage gain, isn't it? Class, you see that, everybody? That's called the reverse voltage gain. I can write it down, but it's pretty obvious. Okay, so that's S parameters in a nutshell. Now we're going to actually have to figure this stuff out for some simple systems to see how it applies. Because you're going to be asked to calculate the S parameters for systems. It's just the way it is. And you have to have an appreciation for this to do any kind of microwave engineering. So I'm going to erase this. And I know you've just been exposed to it. We're going to do a simple one. Okay. Now pay attention to this one because there's one subtle trick that happens. That's something that you don't see unless you're really paying attention. So I have a transmission line over here that's got a characteristic impedance V0. Then I'm going to just put a resistor here, R, right? Not anything else, then I'm going to connect it to another transmission line that has a characteristic impedance V0. And now, I want to find out the S parameters for this system. Y'all hear me on this one? Alright, so this is port 1, this is port 2. The port voltages will be right here, and there will be an incoming V1 plus, and then there would be a reflected one, V1 minus. Here you're going to have an incoming pulse, V2 plus, and a reflected pulse, and this is going to be V2 minus. And now we go ahead and get them. We're going to get the reflection coefficients, then we're going to get the forward voltage gains. Everybody follow this? So when we look at S11, that's V1 minus over V1 plus, assuming that V2 plus is 0, right? Now, here's what it means in a nutshell. It means that the load out here is just going to have a value of Z0, so there's no reflections. That's all it is. Y'all follow me? That way you can't have a V2 plus if nothing's reflected. Everything passes through. When I take a look at this, it's really what? Now just look at this. Here's the reduced circuit. I have Z0 over here, then I have a resistor R, and then I have another Z0 here. That's this port value right there. It's just Z0. And it comes back here, and I want to find out what the reflection coefficient is right here. So Z0 would be over here. And I want the reflection coefficient of port 1. How would you get that? What is reflection coefficient in a nutshell? It's the impedance you're going into, correct? The impedance I'm going into is R plus Z0. Y'all see that? So it's R plus Z0 minus the impedance you came from, which was Z0. This is characteristic impedance. Y'all see that? Minus Z0, right? Over the sum of what? Of both. Y'all agree? So that would be 2Z0 plus R. Y'all agree with that, class? Impedance you're going into minus the impedance you came from over the sum of the two. The impedance you came from. And what's that going to be? That's just R, right, over 2Z0 plus R. Y'all follow me? Now, because you can make that, it's called an argument of symmetry. If I look at this system, if I look at it this way, it looks the same as it does this way. Do y'all follow me? It's a symmetric system. Now, if it had a value like this, if I had another element here, then I couldn't do that. It would look different this way than that way. Do y'all follow me? All right? So, because it is symmetric, it means that reflection coefficient will not only be S11, but it will be S22, because it is symmetric. Does that make sense to everybody? All right? that, we've gotta get the forward and reverse voltage gains. We just need one because of arguments of symmetry. They'll be the same, no matter what you do. So next thing we do is get the forward and reverse voltage gain here. I'm gonna use this one drop circuit. So when I look at the forward voltage gain, what I have to do is this. Now my circuit looks like this. I have this is characteristic impedance Z0. Then I have my resistor R, and I have my impedance Z0 over here. You all follow me? I'm just going to show that impedance here as Z0. And this is port 2, this is port 1. And what I want the value of the voltage here, which would be V2 minus, divided by the value of V1 plus. Now just watch this. This is not hard to see, but sometimes people mess this up. Now, what I really need before I start is I need the reflection coefficient and then the transmission coefficient here. We found out that the reflection coefficient at port 1 was equal to what? R over 2Z0 plus R, correct? You just look at your notes. I know this is new to you, but you all remember that. Now, to get the transmission coefficient at port 1, it's just 1 plus the reflection coefficient at port 1, right? Or, let's say another way, it's 2 times the impedance you're going into. It would be 2 times R plus Z0 over 2Z0 plus R. Either way, this will do it, okay? You all follow me, class? Either one of those two is fit. Now, when I've got V1 plus coming in, the voltage just on the other side of that transmission line, I'll call it V1 prime, is equal to the transmission coefficient of port 1 times V1 plus. Do you all follow me? The voltage here is not the same here because some of that wave is reflected at that juncture. You all follow me? Make sense to everybody? Think about it. That voltage right there is not the same as that because some of that voltage is reflected back. Okay? But some gets through. Now the amount gets through just undergoes voltage division. So we can say that V2 minus is equal to, just take a look at this, it's going to be this voltage here, V1 times transmission coefficient at port 1, and then it's going to be times this impedance over Z0 plus R. It's simply voltage division. After you hop on here, the amount of voltage developed here is just going to be found using voltage division. Do you all follow me? So that means, really, when I take a look at V2 minus over V1 plus, it's just equal to the transmission coefficient of port 1 times Z0 over Z0 plus R. And that would be S21, and in our case, because of arguments of symmetry, it would be S12. Y'all follow me? They will be the same. If you have one, you have the other. Does that make sense? Now that's an example I've done. I didn't put numbers in. I just showed you how you would approach this. A thing you have to always worry about when you do this is make sure you get the transmission coefficient so you get the voltage on the other side of the first transmission. A common mistake is they'll just say, well, this V1 plus is V1 plus there, and it's not. That's the thing you gotta watch for. Okay. All right, it's about quiz. About that time, so take everything off your desk. Set your calculator. I always start over there, I'm gonna start here. Could you put your names on that Smith chart, please?
What is that?